In the second part of this video series on graphics and GUIs, we will explain how to respond to key events and how to use timers to produce simple animations. We will provide an example to illustrate handling each of these events. Because the example that we intend to use to illustrate key events also involves drawing polygons, we begin with a discussion of what is required to draw polygons. Like rectangles and ovals, polygons can be solid or hollow. The naming convention is similar. To draw a solid polygon, we call fill polygon. To draw a hollow one, we call draw polygon. The vertices of the polygon can be specified in two ways. A polygon can be created by supplying all the vertices when it is created, or by starting with an empty polygon and successively adding them. In our example, we will use the second technique. The polygon class contains several overloaded methods named contains that can determine whether a point is inside a polygon or outside. In our example, we plan to use the version of that method which accepts the x-y coordinates of a point. Next, we discuss how to handle key events. In most cases, keyboard input can be handled without providing key event handlers. Text fields seldom need key event handlers, as we have seen in previous examples. Generally, a button click triggers an event handler that then simply extracts the contents of a text field. When it is necessary, key events are handled by either implementing the key listener interface or extending the key adapter class. Like the mouse adapter, the key adapter class implements the key listener interface by providing all empty methods. The three events are key pressed, released, or typed. Key typed includes both pressing and releasing the key. When a key event occurs, it is important to know which key caused it. The event object contains that information. The program that we will use to illustrate key events also involves drawing polygons. It allows the user to specify the vertices of the polygon with successive mouse clicks. Three function keys will control the mode in which the program operates. Typing these function keys will generate the key events. This class contains two instance variables. The first, polygon, is an object of type polygon. Initially, it contains no vertices. They will be added as the mouse is clicked. The second, drawing mode, is a Boolean. It will be true when the program is in drawing mode. It will be false when it is instead in the mode where it determines whether a point is inside or outside the polygon. Let's scroll down to the constructor. Calling the method setFocusable ensures that key events will be directed to this panel rather than the frame it is contained in. The call to add mouse listener is registering the anonymous object that follows as the listener for mouse click events. We are using the mouse adapter to avoid having to provide 4 empty methods. Recall that because the mouse listener interface contains 5 method signatures, it is not a functional interface, which means that a lambda expression cannot be used. When the mouse is clicked and the program is in drawing mode, the add point method is used to add successive points to a polygon. Also notice that it is necessary to call repaint each time the mouse is clicked to cause the paint component method to be called. When the mouse is clicked in the non-drawing mode, what happens instead is the method contains is invoked on the polygon object, passing in the point where the mouse was clicked. It returns whether that point is inside the polygon. A J option pane window is displayed, indicating whether or not the point is inside. Scrolling down to the event handler for key events, The call to add key listener is registering the anonymous object that follows as the listener for key events. As with the mouse handler, we are again using the adapter class to avoid having to provide empty methods. Because we are using function keys, we must use the key pressed method rather than key typed. Because the function keys do not produce characters, pressing a function key will not generate a key typed event. The event that is passed to the key pressed method contains the information about what key was pressed. Because we are interested in a function key, we must use the method getKeyCode to extract that information. The three cases define the actions that need to be performed for each of the function keys. The constant keyEvent.vk_f1 represents function key 1. Similar constants define the other two. The way we determine those constant names is, as always, by consulting the Java API. Here is the section of the API for the keyEvent class that contains these constants. Returning to the keyEvent handler, pressing function key 1 creates a polygon and resets the program to drawing mode. Function key 2 changes the program to non-drawing mode, which allows points to be identified as either inside or outside the polygon. Function 3 changes the program back to drawing mode. After every key is processed, the panel is repainted. Finally, let's scroll down to the paint component method. It sets the color to gray, and then it calls the fill polygon method to draw the polygon. Finally, we need a class that contains a main method that defines the window. It adds an anonymous object of the drawing class to the window. Let's run this program. First, let's click the mouse at several points on the screen. Notice that once we have clicked 3 points, a triangle was drawn. Let's continue to click some additional points. Each time we click another point, the polygon added another vertex. Now let's press F2 and click the mouse again. It tells us whether the point is inside the polygon or not. Pressing F3 will return us to drawing mode. Let's press it and click some additional points. Finally, when we click F1, we will click F1 to start the drawing over. Next, we explain how timers are used. Although timers can be used for a variety of purposes, one of its most common uses is to generate animations. To use a timer object must be created that specifies the interval which indicates how frequently the timer will fire. And as with all events, a listener must be registered that responds to the timer events. As is true with buttons, the listener for timer events must implement the action listener interface, which means that the action performed method will be called each time the timer fires. Next, let's explore how timers are used to create animations. The way that animations are generated is by repeatedly repainting the screen with the sequence of frames that define the animation. The role of the timer object is to periodically call the paint component method to continually repaint the frames of the animation. There are two factors that are necessary to ensure that an animation appears smooth. Each movement should be small. In other words, there should only be a small difference between adjacent frames. Repainting should occur frequently, meaning that the timer interval should be sufficiently short. One limitation is that the interval must be at least as long as it takes to render a frame. With the speed of modern computers, that is no longer much of a limitation unless an image is extremely complicated. Let's consider a simple example of an animation. This program creates a drawing of a circle that is initially very small. It gets larger and larger, and its color becomes lighter and lighter blue until it reaches a maximum size. It then starts to shrink, and its color becomes darker until it again becomes very small. The process repeats indefinitely. This class defines the panel on which the drawing will be done, and the class object will be the listener for the timer that controls the animation. The last two constants in this declaration are the ones that influence the smoothness of the animation. The first of those, increment, defines the difference in the radii of the circles in adjacent frames. Decreasing it will make the animation smoother. The second one, delay, defines the interval between timer events. Decreasing it will also help improve the smoothness. This class contains three instance variables. The first one, timer, is the timer used to control the animation. The second one, diameter, specifies the current diameter of the circle. Finally, the Boolean increasing keeps track of whether the circle is currently increasing in size or not. In the constructor, the timer object is instantiated. Note that registering the listener for timer events is done differently compared to the other events. Passing this as the second parameter to the timer constructor registers the window object as the listener for timer events. The first parameter, delay, specifies the intervals at which the timer will fire. Next, the timer is started and diameter is initialized to the smallest value. Let's scroll down to the action performed method. If the circle has been increasing, it first checks whether its size has exceeded the maximum diameter. If so, increasing is set to false, so on the next timer event it will begin decreasing. Otherwise the diameter size is increased. If the circle has been decreasing, it first checks whether its size has fallen below the minimum diameter. If so, increasing is set to true. So on the next timer event, it will begin increasing. Otherwise, the diameter size is decreased. Regardless of what path is taken, the panel is repainted. Finally, we scroll down to the paint component method. It first sets the color. By using the value of the diameter as the intensity of the blue component, as the circle gets smaller, the blue color gets darker. It then paints the circle. It uses calculations similar to ones we saw with the colorable circle class to center the circle in the panel. As always, we need a main method that defines the window. An object of the circle animation class is added to that window. Let's run the program. Notice as the circle gets bigger, its color becomes brighter. Let's try to make the animation a bit smoother by changing the value of increment to 3 and delay to 25. Those changes do appear to have helped.